So for the others who are not here, we're going to begin our discussion or overview of probability. And let's see how far we get. How many of you have started probability? Or finished, let's say finished probability. Probability spans two modules really, but I did distinctly separate them. So the first module is module 6. And I have the notes, I have some exercises here, and then I have very few pre-edited videos. I just have the live stream from my class, and then I have oh wait. And then I have a discussion of, I have some problems with Poisson and hypergeometric, and I give you the Excel code or Excel formula for solving those. The matter is identifying which you have. If you have a binomial, a Poisson, a hypergeometric, and then identifying the parameters for it. So far in this course, what we have done is we learned about collecting data. Then we looked at how to summarize data in with the 5 features of the distribution. Then we looked at looking at 2 variables and their relationship. And that brings us to here, where we want to go beyond just looking at data and speculating about what it's telling us. We want to get to the place where we discuss questions of inference. Inference is actually testing the parameters of the distribution, the actual true characteristics of a distribution. And so we need to build theory to get to the inference. Inference will be module 9 is where we get to inference. So we have a few modules before we get there, and we begin with probability. Now, we've talked about probability and estimation in the context of the normal distribution. And that's the one we know very well. And that's going to be a foundation for what we do in inference. But we need to talk about a few other things before we get there. The other distribution that we really need is the binomial distribution. So to get us there, we discuss probability theory. Now, probability theory is something we mostly have an innate sense for. So, for instance, when I talk about flipping a coin and the chance that the coin will turn up head, what's the chance that each time you flip a coin, you will see a head rather than a tail?
It depends.
Oh, it depends on
the contour of the place where it falls. Floor, table, chair.
Well, just imagine that it's just in
It's
general.
it could be 50-50, but once you start getting, other contours, then it could vary.
Right, but no, just a flat surface. The chances is 50-50, yes. So imagine if a young person, maybe could be your younger sibling or a son or daughter or a nephew tells you, you know, I flipped this coin here many times. I flipped it 10 times, and each time I flipped, it came tails. Why do they say there's a 50-50 chance of getting ahead when every time I flipped, every one of the 10 times I had a tail? How do you explain that phenomenon?
Yes, because the 50% is based on the population, and he just have a very small sample of 10.
There, that's a good way to think about it. So basically, the answer to him is keep on flipping. You didn't flip enough, okay? You did not observe the long run relative frequency. 50% is a long run relative frequency, meaning you have to observe many repetitions, and of those repetitions, it should be 50%. And here, just to show you, if you did this sort of experiment where you flip a coin once and record what you got, you flip it again and record what you've got, you flip it again and record what you got, and then you compute the average. That's like you're doing repeated sampling to see what you get. So here I just have it flipping once. Hold on. Oh, sorry, I didn't see the chat till now. So here we have it. We're going to flip the coin just once. What happens? In this case, this individual got a head. Then the coin was flipped 3 times. Okay, this is, I think, 2 times. And they got 1 head and 1 tail. So the proportion of heads was 50% heads. Flipping it 3 times, 1 of the times it was head and 2 of the times it was tail. So these are the proportions. This is 1 out of 3, or 33%. And so notice that this is settling the more, just doing this experiment 1 time. So you flip once, you flip twice, you flip 3 times, 5 times, 10 times, and you plot proportion of heads. It begins to stabilize. It's very erratic here, but then after maybe 200 flips, it begins to stabilize. So at 200 flips, 100 are heads and 100 are tails. And it stabilizes. It's not always 50%, but it's very close to 50%. So that is the idea of what we understand to be chance, right? So we want to go through this and build the probability theory so we can talk about other phenomena maybe we aren't familiar with, and we want to describe their distribution. So we learned about the normal distribution, and we use the normal distribution to estimate, make predictions. So now we're going to use probability theory to build other distributions. So we begin with the probabilities. I have to say something about those events. Each time we repeat the flip, each time we repeat the flip, what we are implying is that the chance did not change, right? Each time we flip a coin, the chance of seeing a head is 50%. You flip it again, and the circumstances are assumed to be the same, and you flip it again. This is an example of an independent trial, that each time you observe, it doesn't affect the probability of seeing a head on the next flip. So we refer to events, for instance, I'll just take 2, I'll call one A and the other one B, and I say that they're independent if knowing the outcome A occurs does not influence the probability that the second event occurs. So if you're looking for, so let's define A as a head on a first flip of a coin, and B as a head on the second flip of a coin, then knowing that A resulted in a head does not influence the probability of getting a head on B. Okay. And I'm talking about influence, I'm talking about the probabilities not changing from incident to incident. Okay, so let's talk a little bit about how misuse of statistics or misinterpretation. So you may hear statistics like cancer strikes 1 in 2 men and 1 in 3 women. What does this really mean? Does it mean that one of a group of 3 women will get cancer? How do we interpret these, what would be statistics or estimates in the context of what I've just said before this? So just like the coin not having to be a head, you know, in a small group of 10 flips, it doesn't have to be 5 heads and 5 tails. The sample needs to be large enough, right, to be able to observe long run relative frequency. So it's common in medicine or in the natural sciences when we talk about estimates like these, 1 in 2 men is referencing a large population. So it's really in a population of 100,000, 50,000 men will have cancer in their lifetime. Still sounds horrific, but the point is if you just take 2 men and look at them, one's not necessarily going to get cancer. It doesn't work like that. And similarly for women. Okay, so what about not being independent? What would that mean? How would we describe not independence or no independence? Well, if you are interested in a bag of M&Ms and you're interested, okay, so the bag of M&Ms has 4 different colored M&Ms and you pick one and you eat it. So if they're all different colors, then if it was a blue that you got, then there's no way that the next one can be blue. So the probability of blue begins as 1 out of 4 chances to get a blue, because you're equally likely to get, because they're all different colors. So each one has an equal chance. But once you pick out the blue, you've changed the distribution of colors in that bag. So you cannot possibly select a blue. So now the chance of a blue goes to 0. So this is an example of no independence. Okay, these are not independent selections. A simple random sample, we talk about a simple random sample, SRS. A simple random sample of size n is independent from any other simple random sample of size n. So the sample that you chose does not affect the probability distribution of the next sample that you choose. All right, so we're just going to review a few term, like some, so many of you have intuition for probability. And I want to clarify, kind of do an overview, and I did this in the videos. Looking at this, well, I have it here. Hold on. This overview here. Did any of you see the overview? Because this looks at everything at once, and then I get back into the notes. So I'd like to start here, unless you've all seen it. So should I not do this or do? Mm. Is anybody? Okay, you want me to do it? Someone want me to do it? Oh, I let my iPad run really low. Okay, hold on. Remember when watching my videos, I highly recommend you download to your phone or to your computer or your iPad is the Brave browser. The Brave browser does not have ads, so it's easier to watch my videos. Just changing my microphone. Okay, hope that sound is better. Yes, Naelia. Oh, so people who contacted me about the test, I will be contacting you later about getting it up there. All right, just letting you know. There was some confusion with the timing.
So, Professor, by when would the test grade be available in Moodle?
I'm going to review my grading scheme, so hopefully today.
Okay, perfect. Thank you.
Uh-oh, we have an issue because I did not charge my iPad. See if I can. I'm just trying to connect my iPad. Okay, maybe I can do this in Word. All right, you see the document? So I've identified two events, and I depicted them in this box here. This is called the sample space, S for space or sample space. And the only two possible events, only possible outcomes are either A or B, and they have a relationship. What is the relationship between A and B? How do we refer to the relationship between A and B?
Un revoltillo. Un omelette. Con el quesito afuera. Con muchos vegetales.
Anyone? No idea? It's right there on the page. So we say A and B are complementary. Either A can occur or B occurs, but both cannot occur at the same time. Can someone give me an example of two events that are complementary?
The coin flip.
Sorry?
Flipping the coin.
Okay, so flipping the coin, and what would be the A and what would be the B?
The heads or tails, right?
Right, so either it's head or it's a tail. It can't be anything else. Those are the only two possible outcomes. And that would be just on each flip. This would represent just each flip. So they're complementary in the sense that they complete the space, the possibilities. So let's talk about an event. Let's say A is the chance of rain, and the chance of rain is 30%. From knowing about the chance of rain and knowing that there are only two possibilities, there's rain or there's no rain. Can you solve for these different probabilities? So these are, we're going to consider what's the probability of A and B. And is implying that the events occur simultaneously. When events are complementary, what do we know about them occurring simultaneously? What's the chance?
Zero.
It's 0. So complementary events have a 0 chance of occurring simultaneously. Very good. What about the chance of A or B? What does that mean?
Be 100%, right? Because either or can happen.
So or implies this or that. It
Yep.
either rains or it doesn't rain. Doesn't that capture all the possibilities? So that's 100% chance of one or the other. And what about neither of them? What's the chance that neither it rains or doesn't rain happens?
Would be 0 also, right?
It will be 0 because one of them has to happen. Okay, so it's a very simple example to describe it. By knowing that two events are complementary, you know a lot. You know a lot. You know, no matter, even if I know 30% for A, I don't need that information to solve for those probabilities. I already know those probabilities. Okay, so now you think you know that. Let's go on to the next relationship between two events. So here's two events, A and B. Now, A and B are not complementary because they do not completely fill the space. There's event A, there's event B that are of interest, and then we don't define anything other than A and B. So we have an area here. What should we call this area back here? All the possibility of things that we haven't named out here. We're going to call this not A or B. So that's what we reserve this discussion for, this event. So we have A, B, and then outside here, we're not going to be specific because we really want to focus on A and B, but we're going to call the area outside the events not A or B. So you could have some sort of service in a company. So you attend, you know, I use the example of a beauty salon because I used to teach nursing students statistics. And in a in a salon, beauty salon, you could have one service, you could have another service, and then there's a whole other bunch of services that you might have, but I'm not going to name them A or B or any letter. Okay, so let's say the chance of having service A is 30%. The chance of having service B, so A could be, I say, manicure, and B could be having your hair colored. And then there's a bunch of other things. But knowing these probabilities, again, I have immediately some knowledge of what to expect. A and B here are known as disjoint events because you do not, in this depiction, the services are not had at the same time or in the same visit. Okay, so it's possible that the services just so expensive and people don't want to do them at the same time, or has to do with the demographics, or it's just such a busy salon, you can't have time to do two services at a time. Whatever the case, in this depiction, A and B cannot occur at the same time or during the same visit. All right, so now with that information, can you find the chance of A and B, the chance of A or B, and the chance of not A or B for an individual visiting the salon on any given visit? I'll give you a moment for that. So what's the chance of A and B? Oh, Marcos, the area outside is called not A or B. Okay, so A and B, the chance of both A and B happening together by the definition is 0. There's no chance because they're disjoint, they never cross, they never occur together. What is the chance? Oh, I moved my B. What's the chance of A or B? So I'm just appealing to your intuition and your knowledge of probabilities to date. Okay, I'm going to get into the more details as we progress through here. Okay, so Maria said 70%, Gloria said 70%. How do you know it's 70%?
You add them up, 30% for A and 40% for B.
So because they do not overlap, I can just say the chance of A or the chance of B is just their sum. Okay, so when the events are disjoint, you can just add them up, and that is 70%. So when events are disjoint, you can just sum them like that. Now, the next one is saying go for the outside part. So we call that not A or B. So neither A nor B. And to get this, since we're just summing these areas, then this outside area, because the entire space should be 100%, we should subtract A and B, and that will leave the remainder. So that's what we'll do. Not is 1 minus probability of A or B. So that's going to be 30%. So I'll write 30%. So that could be having a facial, it could be having a pedicure, it could be in this example of the salon, the beauty salon. So this is pretty straightforward. I'm just doing some housekeeping, checking that you understand these terms. Any questions so far? What I want you to do for a moment is look at the disjoint and compare it to complementary. Is there a relationship between disjoint and complementary events? You can see that complementary events are disjoint. Do you agree with the statement? Complementary events are disjoint. They do not overlap. And we know that their probability of occurring together is 0. So just like complementary, or just like disjoint, complementary events, A and B is 0. But disjoint events are not complementary because there is an outside part. All right, there's something else that can happen. So disjoint events are not complementary. That's why I have to teach it. Okay, no questions so far? I'm just gonna move these a little closer together to get everything on one page. So I have two other relationships that we're gonna discuss. And the last two look the same, don't they? Both demonstrate A and B overlapping. And there's a section with where they overlap. What should we call the section where they overlap? Should we give it a name? What should we call it? You can see my cursor, I hope. I'm hovering over the space. Right, Maria, or Marla. Sorry, my glasses are not on. Marla. Yes, we're gonna call it A and B. So A and B is the overlapping part. Do we know the probability of A and B in this first diagram?
$70%?
No, but it's not.
No, you did the overlap, sorry, the overlap, no.
But for the overlap, I give it to you here. I tell you that it's 10%. I have to give it to you. Otherwise,
We wouldn't know.
you wouldn't know. So now that we know this overlapping piece here, trying to write it, but okay. So you know the overlapping piece. Do you know the next one, A or B?
I guess you add A and B and then subtract the A and B part, the 10%.
So we have to do that because of why?
Because it's overlapping.
Because it's overlapping. We're going to add A and we're going to add B, but then we added this too many times, this space. So we need to subtract it. So we're going to write A plus, so obviously you need to know the relationship between events in order to determine their probabilities. That's another lesson of what comes from here, from this discussion. So when you take A and you add to B, it's 70 minus the overlapping, leaves you 60%. Is everyone okay with that? It won't let me bring it. Okay. And now that we have this A or B, we can determine again what the outside events are. So back to the salon, A could be a manicure, B can be hair color, and A and B are people who had both services. And then there's all the other services outside, which could or could not overlap with these other ones, but I'm not defining them. They're just out there. No, we're not focusing on them. So not is just 1 minus probability of A or B. So I just subtract. So not is always 1 minus. It's like the right-hand side in the normal distribution. It's the 1 minus. So this makes 40%. Okay, so all of this was pretty straightforward. You can use intuition, arithmetic, and you learn some terminology for the 3 types of relationships: complementary, disjoint, and overlapping. Then I introduce another pair of events, and I tell you that they are independent events. How does that change things? What does independent mean? It means if I know one event occurred, it doesn't change the probability distribution or the probability of the other event. So if I'm in A, the chance of B occurring doesn't change. If I'm in B, the chance of A occurring does not change. Now, that is not necessarily always true. That's why we define independent events. Now, in statistics, having events independent simplifies the mathematics very nicely for the purpose of theory. So that's why I introduced the idea of independence. But it's not common. I wouldn't say it's common that events are independent. So in the context of the salon, if A is a manicure, and I know that someone had a manicure, does it change the chance of them having had their hair colored? Well, let's say they're independent and it doesn't change the chance that they have their hair colored. Then it's possible that money is no object and there's enough capacity or resources in the salon to provide me both. So in that case, they were independent events. But that's not necessarily the case. It could be that money does have its limits, and once I have one service, I do not get the other. Or once I have one service, that takes staff away, and there's no one to provide the other service. So in this case, I've told you A and B are independent. It still looks like the exercise over here. Now, the drawings are not necessarily to scale. So don't try and figure out areas mathematically. That's not how we look at these drawings. The drawing is just to show you the interrelationship, not the size of that you can estimate probabilities. And you're not going to shade the area and try to estimate the area. The idea is A and B are overlapping because they are independent. Independent events overlap. Independent events are different from disjoint events. Okay, so the words are very specific. Disjoint events do not overlap. Independent events do overlap. So here's the information I give you the chance of A is 30%, the chance of B is 40%. So I'm staying with the numbers I've used before, but I do not tell you what A and B is. I do tell you A and B are independent. So what do I know about the intersecting piece? What do I know about this intersecting piece if they're independent?
Well, it can happen. Doesn't matter if one or the other happen, right?
What I know is that, okay, so I'm going to be more specific now because this is the one that where the learning takes place. So if I am in A, so this is A. I want to figure out the chance of being right here. So the chance of being in A multiplied by the chance of B, given that I'm in A, that is actually what A and B means. Okay, so now I haven't mentioned that before, but that's how you would figure out A and B. So up over here where I did this, this was actually probability of, so this means B given A, so that you're in A, the chance of B, you multiply it by the chance of A, or you could also compute it as being in B so you're in B and of those events, the probability of B times the probability of A given B. That's what that line means. That line means given. So over here, back down here, if I think about it, so I could write it either way. I could calculate it either way. Now, over in the independent case, what did I say about what independence means? It means that if I'm in A, it doesn't matter the chance of being of it being B doesn't change. So it doesn't matter if I'm given A. The chance of B occurring doesn't change. It's still 4%. So this becomes and that's the very fact that the probability of B given A is just B. It doesn't matter that A occurred before. Now, that's not necessarily the case. Like I said, things might change because I already spent money and I don't want to do my hair coloring anymore because it might change the probability that I get or people get a hair color. But in this case, I've said they're independent. And so it just reduces to that. So in the case of two independent events, to find the probability of both of them coinciding or occurring together, you just multiply the probabilities. And that's 12%. So I take time to explain this because some students statistics before and they don't know why they multiply. I'm trying to put it all in one line. All right, but that's why you multiply, because A and B are independent. It doesn't matter that A happened. The chance of B occurring does not change. So like I said, people have enough money, money is no object. And just because they spent money on the first service, it's not going to change the chance of them obtaining the second service. Any questions about it?
So the difference between the previous is that even though it's overlapping, since we didn't know that it was independent, you had to give us the probability of A and B, and in this case, we can calculate it.
Exactly. So for the first one, I didn't know, there's no way to know A and B, and I'm glad none of you told me to multiply them. But students will, they think you just multiply them. No, you cannot multiply those probabilities unless you have that piece of information that they're independent. So instead, I gave you the value as 0.1, and then you could calculate the other probabilities. So sometimes the symbol for and is they use like an upside down U for intersection, and for or they use a U for union of the events, just to tell you there's some different symbols you may see. All right, so for the case, the independent case, case number 4, calculate the probability of A or B, and then not A nor B. Yeah, so this term, this conditional probability, is probability of B given A. Is conditioned upon. And notice I can write it either way. I should be able to get the same answer. Probability A times the probability of B given A, and then that should be the same as probability B times the probability of A given B. Either way. Oh, I did too many things and then I lost my letters. All right, so let's do the last ones. Oh, Marla got them already. So A or B is again probability of A plus probability of B minus the overlap. So it's the 70% minus 12%, which is 58%. And then not A or B, or neither A nor B, is 1 minus. Okay. So I've talked about the different relationships. And I spent some time on independent and showing you one thing, that independent events are not disjoint, they actually overlap. And very specifically, I could find the intersecting piece, the chance, by just multiplying A and B, because the conditional probability reduces to the probability of the event, because it doesn't matter that one event occurred, it doesn't change the probabilities at all. So that the sort of new thing here that maybe you've never seen before is this. That the probability of A and B is equal to either the probability that one event happened multiplied by the conditional probability of the other. So that means when I gave you 1% here, or sorry, 10%, 10% is the result of multiplying these together. So you could actually find the conditional probabilities because you have A and B. Let's see if we can do that. So looking back at the overlapping, if I asked you to find probability of B given A, what is that? And what is the probability of A given B? Can you do it? So because this whole thing is equal to 10%, and we know probability of A, then it's just 1 divided by 3. Which is 33%. Are you following me? So you could find the conditional probabilities if you wanted. And A given B in the similar way. So the way that you write this is like, just write, if it's easier, say I'm in B, and then the chance of the other one given B. That also should be 10%. So then this must be 0.1 divided by the probability of B. So you should be able to find those. So the chance, so what happened here is the chance of B, once A occurs, it went from 40% and it went down to 33%. So it's a lower chance. And the chance of A occurring if B occurred, it went from 30% down to 25%. So you can recover those probabilities if I did the math right. Does it look good, Marla? Did I do it right? Okay, so I don't spend a lot of time on conditional probability. But I use it as though I can refer to it. So I hope you're comfortable referring to conditional. And I cannot per se draw it. That's the reason why it's kind of hard to understand, because I can't really draw it. But I'm drawing it this way and saying that there's a difference from this overlapping one to this independent one because the probabilities changed. A changed to A given B, B changed to B given A, and they went down. So you can think about it as because money, the spending affected the chance of the events occurring with the same probability. All right, so I've sent a lot. I hope that's not confusing. You guys can let me know. Let's see what else we can look at here. The takeaways are that you can't just multiply two probabilities to know about their intersection. That's reserved for specific case of independent events. Okay, let's go back to the notes. Okay, are there any questions about what I just discussed? I use I proceed with a number of examples. All right, so I started kind of in the middle. And then I take some time and I go through in this discussion. Can you see my screen? Let's see. So I I lay out some of the terminology. And then look at probability rules. See if I do that right after. Yeah. Okay, so this is my first example is looking at the experiment of flipping 4 coins, not just 1, but 4, and the possible outcomes. Now, here is the sample space of the outcome. So there's a discrete number of possible outcomes. There are 16. And the H represents the head turning up, and the T represents the tail turning up. And that's all the possible, so that's the possibility of all results there. We refer to the experiment, flipping 4 coins. The variable is X. X varies. It's the outcome of flipping 4 coins, and X can become either H, T, etc. So these are the values, or these are the outcomes in the sample space. The probability distribution refers to, again, what is the distribution? It is the possible outcomes and their probability. So I've listed all the possible outcomes, and each one has a chance of 1 in 16 because they're all equally likely. There are 16 of them, so their chance is 1 out of 16. And that's because the probability space S must have a full or complete 100% of the possible outcomes. So 116 times 16 is 100%. As we discussed earlier about variables and values of variables should be numbers. So I could change H to be represented by a number, and I could make it represented by 0 if I really wanted. I could do that. But for the illustration here, I'm just going to leave it with the alphabetic letters. Okay, so those that's my first example of an event, and I defined the variable X, and the I've defined the sample space and the probability distribution. Now I'm going to introduce a second example. This example, it defines X, and it is referring to the previous 4 flips of a coin, but I'm going to define X differently. I'm going to define it as the number, hold on, let me see, the chat disappeared. Let me get the chat back. Someone was asking about, oh no, okay, we're good. So X is the number of tails in 4 flips of a coin. So I'm going to be taking the possible outcomes and sorting them. There is only one occurrence where there are 0 tails. There are 4 possible outcomes that represent 1 tail, 6 possible outcomes that represent 2 tails, and 4 possible outcomes that represent 3 tails, and 1 possible outcome that represents 4 tails. So I'm going to use 0, 1, 2, 3, and 4 as my values, but the phenomenon above in example 1, I'm going to use to estimate or calculate the probabilities of each of those outcomes. So since it's one possible way out of the 16, the probability of 0 tails is 1/16. The possibility of 1 tail is 4/16. The possibility of 2 tails is 6/16, and so on. And so that's what I put here. And I write them, I show you how I express it in notation, and you should feel like it looks familiar, right? This looks like the normal distribution, but I define X differently. X is a discrete distribution, and this, as opposed to 4 pages of the normal distribution of tables that I've given you, there's just how many outcomes? 1, 2, 3, 4, and 5 possible outcomes. These are their probabilities. I can write it as a fraction. I can write them as a decimal, but they have to sum to 1. So now that we're here at this point, so I've introduced a different table than the normal distribution, but I can ask similar questions. I can find out what's the chance of seeing observations lower or higher than a certain value. With the Z table, you talked about the Z score being lower than C standard deviations from the mean or higher than C standard deviations. Now I'm going to talk about being having more than 2 tails. So if this says at least 2 tails, so that means I have to use the table with 2, 3, and 4, and I just add those together. So I show you here, these are the possible outcomes that I'm able to list because it is a discrete distribution. Now, this is different from the normal because I cannot write down the possible outcomes. I mean, it's a long, infinite number of possibilities, right? But I can actually list them here. So I square off the ones I'm interested in. At least 2 tails is 2, 3, and 4. So what is that probability then? So you sum 2, 3, and 4 for 11/16. That's right. So you can write it as a fraction. You can turn it into a decimal. And then you can do the other ones. So this is less than 3 tails, less than, so that means 0, 1, and 2. So you could write it probability X equals 0 plus probability X equals 1 plus probability X equals 2. So I don't expect you to write it all up. But I want you to understand what you're doing. What is it that you're doing behind? What is your assumption? Well, you assume. Well, let me ask you, what did you assume in doing this addition? You're assuming disjoint events, right? You're assuming that they cannot happen at the same time when you're adding them like that. That's what you've assumed. It's only one or the other. Or it's one, only one, mutually exclusive or disjoint. Then I can ask you, less than 1 tail or more than 3 tails means less than 1 is 0 and more than 3 is 4. And when you add them, you get 216. Okay, so I just want you to realize, very good, Marla. I want you to realize that we're doing the same sort of thing that we did with the normal, where I give you the parameters and then you can use it to create a standard normal and go on a table. In this case, I give you information, you can create the distribution and answer questions relative to the possible outcomes here. All right, so we have some terminology. I talk about an event as any collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. And a compound event is an event combining 2 or more simple events. I'm not going to quiz you on the terminology, but just so you can read and know the vocabulary. And the sample space for a procedure consists of all possible simple events. That is, when we write the sample space, we prepare it so that they can't be broken down any further. We get into the simplest depiction of the events. Then I do an overview of the rules of probability. There are 6 rules, and we've used them all so far in our overview and then my little introduction. Rule number 1, all probabilities are between 0 and 1. They cannot be negative. They cannot be more than 1. Rule number 2, all possible outcomes together must have a probability of a 1 or 100%. Rule number 3, the complement rule, which we used, and I introduced some notation. Rather than calling it A and B, I'm going to refer to A in terms of its, or the complement in terms of A. So it's going to be A and A complement with a little C superscript, or I can use a bar to say not A. So those are all not A happening. And I just referred to some of the example using the previous example. Then there's the rule of disjoint events. So if events are disjoint, then you can calculate their union by just adding their probabilities together. And then I have an exercise here to test you on the first few rules. So why don't you guys try this and get a glass of water. So try this exercise here. This is about a doctor, and the doctor can either be in his office or in the hospital. And we assume that he could be other places. So we're going to say they're disjoint with other possibilities, but we're going to define A as the office and B as the hospital. All right, you finished the problem? Okay, so the best way to approach this, since I know it's disjoint events, is to depict it as such. Let's do this. I'm going to cheat and get this drawing over here. Okay, so 48% is A. And 27% is B. So what is the outside part? Let's just define all our spaces. So the outside part would be so that begs the question, A or B would be the sum, right? So A or B is the sum, which is going to be 75%. And so this is 1 minus 75%. Which is 25%. So I define all my space, A, B, and the outside. So now let's see if we can answer the question. What's the probability that the doctor is not in the hospital at 9:30? So B is the hospital. So not in the hospital, probability of not in the hospital is not B, which you can write as probability of B C, or you can write it as the probability of not B like that. And it's basically 1 minus the probability of B, which is 0.73. So then the next question, so we're going from these symbols into word problems, all right? So let's see, what is the probability that the doctor is either in his office or the hospital? So that is just the one we already calculated. That's the probability of A or B. That's how you would say that, either office or hospital. And the chance is 75%. Sorry, did I disconnect for a second?
Yes.
Okay, you're back. All right. So the probability that the doctor is either in the office or the hospital is just the sum, because they're disjoint. I just added. Okay, what if the doctor didn't go to his office or the hospital, he is at home? What is the chance he is at home?
Well, we don't know because we don't know everything that's outside of the 75%.
Well, they've defined it that way. It just says, so you go by they've defined that this represents A is office, B is hospital, and they tell you that if he's not an A or B, then he's home. So all of that space is now defined as home. What is the chance he is at home? Remember, we're talking about 9:30 a.m. It's a very specific point in time. It's in either three places. So that's going to be what we already discussed, probability not A or B. 25%. Is that okay with everyone? I got it by doing 1 minus probability A or B, which we already calculated in the other part. Part B. All right. Then I have a lengthy discussion just to review the whole idea of long run relative frequency and independent events. And I talk about the conditional probability, so you can review that. And that brings me here. Let's try this exercise together.
Professor, in the previous exercise, where do you say that they established that the remaining 25% or outside A or B was the home? Because I didn't see it on the.
Right here in C. If the doctor didn't go to his office or hospital, he is then at home. It's just established there.
Mhm.
Yeah. Okay. So let's define X as the number of tails in 4 flips of a coin. And so think about the example I showed you before. And define A as observing 2 tails in 4 flips of a coin, and B as observing less than 3 tails in 4 flips of a coin. So I have depicted A here and B here. So now I've redefined the sample space of possible outcomes in terms of A and B, although there's other things that can happen. Can you draw A and B in this space? So out of this list, I just put it there just to remind you. So out of these possible outcomes, sorry, it's very small, but if you remember, I'm going to define A as just 2 tails and B was defined as less than 3 tails. So how would you draw A and B in this space where all possible outcomes are these here? And I just want like just a shape, like an A and a B blob, a shape, not a. Don't write out these exact outcomes.
A is part of B, so it should be inside B.
Exactly. So A is part of B. So if I make B like this, then A should be inside. Is everybody okay with that?
Yes.
That's how we resolve the issue. So in addition to the 4 cases that I showed you, complementary, disjoint, overlapping, and independent, we have a 5th relationship between A and B, 2 events. And this is one that is completely contained in the other. So because this is like our 4th in a series, or sorry, the 5th, let's do the same that we did before. Find A and B probability, find A or B probability, and find probability of not A or B. So make sure you read through the notes because I did skip some parts. I mean, I'm not skipping, but you can go deeper with those other parts. So A and B is the intersection of A and B. What would that be? Where do they intersect? It would be the same as A. A or question? A or B would be the union of them. Well, we don't want to overlap, so even if we added A and B, we'd have to subtract A. So really, it's just probability of B. And then not A or B is really just 1 minus probability of B. So it's 5/16. Without knowing the drawing, if you were just to add A and B, you'd be in trouble. Because A and B, if you add them, you get more than 100%. You 616 plus 1116 is more than 100%, right? So something's wrong there. Well, what's wrong is that you've ignored the fact that they're overlapping. You have to know their relationship to be able to solve for probabilities. You need to know their relationship. I think that's another takeaway for you. In addition to the rules that I've taught you and their applications and the terminology, you need to know the relationship of variables or events, sorry, to be able to think of their combination and the probability of their outcomes.
Yeah, this is an overlapping, but it would be considered a compound event, right? Because one is within the other.
I refer to it as a contained event. I think it's completely contained. So it's not exactly overlapping, but it is like you're gonna treat it like it's overlapping with the rule. You can't just add them. They're not disjoint anyway. So
Right.
the overlapping rules apply.
Yeah, for sure. But it's calling it a compound event on the example, right?
I'm referring to them as compound because I took the simple events and I put them together. That's why I call them compound.
So what would be the wording? You mentioned another word.
I said contained, A is contained in B. Completely contained. But the overlapping rules apply. What's different is the way the way that these reduce, A and B just reduces to A or B reduces to B. That's unique to the others, against the others we looked at. Okay. Let's see what else we can do. All right, so we have, so we know these rules. I've only discussed 4 of them. There are 2 more that you've already applied. But to get us there, I want to talk about a couple of other things. Okay. All right, so here you have, again, a discrete distribution, a discrete again, because I can list the number of outcomes. But I have 2 different distributions. This is a joint distribution with 2 variables, class and gender, or job class. Let's say job class and gender. So let's see what we can do with this exercise here. What it shows you, we've divided occupations into 6 classes of occupation and 2 genders. So you can notice that there are some where males dominate and females do not in this class D. Also in E. So those, otherwise, okay, well, B as well. So in B, women dominate, but I mean, it's a greater preponderance of women in that occupation class. And in D and E, it's more men. Okay, so you can think about where you would see that. In finance, you find disproportionately more men. There's more and more women in science and the STEM fields now. Where they're almost equal could be in a teaching profession. These days. So what about in medicine? So in healthcare, you're probably more likely to see women as nurses specifically, right? So for support staff in healthcare, it's going to more likely be women. But then doctors may be more likely to be men. So these kinds of distribution of gender has changed over time, right? But right now, this depiction here of this is the distribution of a population. I'm not going to be specific, but in this population, we have divided our classes into 6 and gender, and we see some variation here. All right, so let's verify that these probabilities are legitimate. So what would make them legitimate is that they should total 1 in this joint distribution. So you can verify that, and a way to not waste time is to do it by gender. So if you add up going this way, what do you get for males? So I can define that for males, for women. What's the chance of being a male in this population? No comment? Did I lose you? %60%? Yeah. And then you should add across here to make sure it's 40 to verify the legitimacy of the probabilities. So it is 40%, so that makes 100% total. So this looks good in terms of the values assigned. Whether they're correct or not depends on your sampling and all of that, right? Representation. Okay, so let's see, what this is called is, that's the probability of being male and in occupation class A. If I go down here, I'm going to call this, I could call this probability of being in occupation class E, and I can add that up and make it 0.14. Now, what's not on this table are conditional probabilities. So you don't see them directly, but you can compute conditional probabilities from this table, saying, given I'm in C, the chance that it's male. That's a different thing, and you don't see that number here. Okay, so everything in here are ands. They're the intersecting events. Conditional probabilities can be calculated okay, it's not on the chart of probabilities. These are called, these ones where I sum across or down, these are called marginal probabilities. Again, vocabulary, I don't really get into, but it might make your reading easier. I'm not going to test you on the terminology, but it's good to know. Okay, so these are marginal probability because they're on the margin. The margin. Okay, so conditional probabilities are not on the chart, but you could derive them. All right, so yes, this is 100% in total. So yes, legitimate. What is the probability that a worker is female? We already figured that out. That's 40%. What is the probability a worker is not in F? So probability of F is, we know we just add together going down 0.03 plus 0.01, and it's 4%. But not F is 1 minus F is 96%. And then to be engaged in D or E, the probability of D or E, how will we figure that out? Are D and E disjoint? The way I've derived this chart here of probabilities or the joint distribution, they are disjoint, so I can just add them. D is 14%. And so is E. Looks a little messy. So it's 28%. Okay, questions about this joint distribution? And it's a discrete distribution, right? Joint distribution, it's discrete because I can list all the possible outcomes in a chart. When it's not possible to put a chart on them, it's continuous, right? We have to make a whole set of tables or a formula that helps us develop the function, and then we can calculate the probabilities. So that's different. Now we stay away from that in this course, I'd say, unfortunately, because I cannot assume your strength in calculus. But so I stick with discrete distributions, but you can also do this with continuous distributions. Like the normal distribution.
All right. So again, the same chart, our joint distribution. I'm reading off the chart, occupation A and woman is 8%, male and woman, like they cannot be at the same time, that's 0. And D and male is 13%. So that's how you read the chart. And now I have the question. So all of that was easy and straightforward. Now I have a question for you, a real question. Are occupation A and being female independent events? How will I figure that out? What does independent means? It means if I know that the person comes from occupation A, it doesn't change the probability of their gender. Now, in general, that's not necessarily the case. If I know that someone comes from health service support, like being an admin assistant or being a nurse, it's more likely they're female, right? So that's not necessarily independent, but it could be independent in other professions, in other occupation classes. So let's see, how would we figure out if A and is occupation A is independent with gender? The easiest way to do this is just to assume that they are. So assume that A assume that they are, and then find evidence that they're not. So if they're independent, then this has to be true, correct? So let's check both sides of this. Let's check the left-hand side. What is the probability of A and woman? That we read right off the chart. That's here. That's 8%. And now let's check on the right-hand side. What's A? What's woman? So let's begin. What's the probability of A? Right, so I've calculated the probability of A and the probability of woman. Let's put them in the exercise here. So this is 0.2, this is 0.4, which makes 0.08. Aha. So I assumed they were independent and I wrote this statement, and now I found out that in fact they are equal. So you can say since the left-hand side equals the right-hand side, yes, they are independent. And that's all you have to do. So just verify that it's true. What's another way that you could do this? What is the idea of independence beyond this verification? It means that if I am in the subset of occupation A, the chance of a woman should still be 40%. Out of these two, so if you rescale this to 20%, this is just 20. Is 8% of 20 exactly 40%? That's what you're checking, that the probability of being a woman in class A doesn't change from 40%.
Yes, it is 40%.
Exactly. So what did I do here? I'm looking at we'll do it up here. I'm working backwards so you can understand. So what I said was check and verify that in the subset of A, so just looking here, I'm rescaling, is the woman's probability
That's 0.08 over 0.20.
is it 40%? Yes, it is. So okay, so the probability of being a woman inside of A is the same as being a woman in general. So the probability didn't change, and that's how I know they're independent. Questions about it? Okay, so I go to the subset here. This is 20%. Inside of that, 8.08 out of 20 represents 40%. So it's independent. All right, so so rule number 5 is all about the multiplication rule for independent events. And this is where I discuss or remind you that events A and B, the probability is found as a multiplication of A's probability times the probability of B given A. So I'm in A times, so I'm in A, the chance of B in A times A should be the probability of A and B. So over here, that would look like well, it's confusing because I'm using A and B's and these are all, but the idea is being in the subset. That's the idea of being in the subset. So really, if you can rewrite this so the conditional probability of B given A is the same as both A and B occurring inside of A. It's what I did above. But it turned out that B given A, whatever I calculated, was exactly the probability of the other event, the woman. If they're different, then they are not independent. If they're the same, then it's independent. So remembering this in general, which maybe you don't remember or you learned it in statistics, that is in general the definition of two intersecting events. Probability is the probability of the first one times, given the first one, the probability of the second one, because you're saying out of those times, what's the chance that the other one occurs? That's how you figure out their joint probability. That's also that can also be extended it can also be written like that. Those should all be the same number. So what we just did above was calculate the probability of women given event A, occupation A. That's what we did above. So we did this ourselves. All right, so if the events are independent, then the conditional probability, it doesn't matter if A happened, it's just the probability of B, doesn't change. So in summary, for disjoint events, you add probabilities. For independent events, you multiply them. Then I have some exercises for you to try that I will ask you guys to try. I'm pretty sure I solve them. Yeah, every time I write this, it means I've solved them online. So you have the video solution of this exercise. Okay, so make sure you try that because I bring it up again later. And finally, yes, the sixth rule is that basically we were using this all along, but you have to subtract off the overlapping piece when two events overlap and you want to find out the probability of either of them occurring. And we figured out how to calculate A and B if they're independent. If they're not independent, someone has to give you more information for you to calculate their intersection, the probability of their intersection. All right, so that is that for probability unit or module. I have them numbered differently from before, but this is module 6. Now here is where I start module 7. So module 7 is discussing the different kinds of distributions, and I use the same set of notes. And there are discrete distributions, there are continuous distributions, and I review which ones we're going to focus on in this course. There are the general discrete distributions where I just give you the possible outcomes, their probability, and that's it. So you've seen this kind of thing, a table of values. In this case, the variable X defines the month that a robot arm will break down. So if it breaks down, the chance that it breaks down in the first month is 5%. The chance that it breaks down the second month is 25%, and so on. We can depict that graphically, just like a normal distribution where we plot in the graph that you guys see for the normal distribution, you plot the z-scores here, and then the frequency or relative frequency in the curve. Here we have the relative frequencies, but there's no density, there's no area on it. There's just either 1, 2, 3, or 4 occurs. And the height of the curve represents the frequency, not the area, right? So yeah, it's a little different, but the same idea that I can give you a table and I can give you a chart, and then I can ask you questions with this newly defined variable X. I can ask you questions about when the arm will break down. So I can write something like, what's the chance that X is greater than 3 or greater than or equal to 3? So that says, what's the probability that the robot arm will break down in the 3rd or the 4th month? That's what it means. And then you just have to add the probabilities to make 70%. Okay, so because they're disjoint, you can just sum. Here you have the second type of discrete distribution we're going to focus on in this course, and this is the binomial distribution. We need it for inference, so we're going to study it and know it well. Here is an example of the binomial distribution. You remember the exercise where X is defined as the number of tails in 4 flips of a coin. X is actually a binomial random variable. Here is the table of values that we derived earlier, and here is the graph, and you notice that it is symmetric, right? So we have a very symmetric distribution. Now, a binomial does not have to be symmetric, but a binomial will be symmetric in a few cases, and we're going to discuss those. One is where the probability, well, I have to define the parameters, so let's do that after. And I'll talk about it after. Okay, so what defines a binomial? Binomial distributions satisfy 3 criteria. First, we define in general X as the number, so it's counting the number of successes out of n independent trials, and the X, it represents the successes. So for instance, flip a coin 4 times. In that example, n is 4 for flipping the coin 4 times. And the number of successes, we're counting how many heads. We define success as a head. So we're looking for something in particular, and we're going to look so many times. So while we're doing that, if it is the case that each observation has only 2 possibilities, it can be what you're looking for, we call it a success, or it's not, which we call a failure. It satisfies criteria 1. If we know P, the probability of observing a success on any of the tries, then as long as P is the same for each trial, then this satisfies criteria number 2. So you need to know the probability of success on each try, and it doesn't change. So again, for flipping the coins, that's true because you know the chance of a head, and the chance of a head doesn't change from flip to flip, so that satisfies too. And finally, for the third criteria, the trials need to be independent, so the probabilities do not change. The probability of a success doesn't change from flip to flip or trial to trial. And we know how many times we're going to flip, and we don't change it. It's a known number of flips. If criteria 3 is satisfied and the other 2 are satisfied, then what you have is known as a binomial random variable. So that's the P. It turns out if P is 0.5, you will have a symmetric distribution, just like we do here, but it's not necessarily always the case, okay? Because N and P will describe the shape of the distribution, we're going to refer to N and P as parameters. They're characteristics that describe the distribution and help us in making estimates of what to expect. So we write X distributed, remember this? We did this for the normal and the standard normal. X distributed binomial with N and P. N is the number of trials, and P is the chance of a success on any independent trial. So for instance, find the probability of seeing more than 5 people holding an umbrella on a rainy day. If 100 different people are randomly selected and observed having an umbrella or not, the probability of holding an umbrella on a rainy day is known. It's 10%. So this is our P, the chance of seeing what we're looking for. This is our N. It's how many times we look. And so we can write X, well, we can define X as the number of people that carry an umbrella on a rainy day out of 100. So this is, again, our N independent trials. And this is our success. Carry an umbrella. All right, so what does it mean for this to be independent? What has to be true for these to be independent? Give me some examples where it wouldn't be independent. Observation or trials. Well, what would it have to be independent? What would have to be the case? Okay, so Marla said, so if one person has an umbrella, it doesn't influence the chance that another person has an umbrella. That's what it should say. Okay, so it doesn't influence the chance that another person has an umbrella. It doesn't change the probabilities. Now, you have to then look at people in groups, probably one person per group, because people share the umbrella, right? So you'd have to look and just pick one person out of the group. You can't pick 2 people out of the group because the probability they have an umbrella probably is changed from the general population of 10%. Because someone will say, ah, did you bring the umbrella? Yeah, I got an umbrella. You don't have to bring yours. So it affects things. So very good, Marla. So, okay. So, let's review the criteria. Criteria 1, either you have an umbrella, you see an umbrella, or you don't. Criteria number 2, the probability of success in any single independent trial is known. Notice that information needs to be provided, right? We need to have that information previously given to be able to define this as a binomial distribution. And 3, you know how many trials, there are 100, and that's it. And they are all independent. The chance that somebody has an umbrella does not change from observation to observation. So make sure you observe people, singular people, if you're gonna observe a group. So then we write down X is distributed with N and P. I'm just using alphabetical order, N and then P. And then finally, because I have that, I can now answer the question. So why is it that I think I can answer the question? Well, we could use Excel to generate the probabilities. I'm going to show you the formula for binomial in the videos. You'll see that when you start, if you have already begun your binomial distribution review. But I'm going to show you right now how to do this in Excel. The initial question is, what's the chance that more than 5 people out of 100 will have an umbrella on a rainy day? In other words, we write P, and sometimes I write PR, sometimes P. Don't let that confuse you. But this just means the chance that more than 5 people have an umbrella, where X is the number of people who have an umbrella on a rainy day, with N equals 100 and P equals 10%. So if we go to Excel, and oh, I never turn that volume down. Let's do this. All right, so I'm going to say binomial. You see how many things show up? All these different binomial, hexagon, octagon, all these things. Okay, all I want is the distribution. Binomial dot dist. Let's try that. You can look all this stuff up on the internet. Now let's open up. Something's wrong. Oh, I have to pick one. Okay. So I'm going to pick this one, and it asks me for the number, the trials, and the probability. So the number is the actual thing you're looking for. And in our case, we want to look for less than 5. So it happens that it will give you the cumulative up to 5. So that's going to work for us. So, but we want to go greater than 5, right? 5 or more. So let's remember that that 5 is for less than, just the left side. There's going to be 100 trials, and the probability of success was 10%. So I'm going to put 0.1. I think that's right. And then I want it to be cumulative. And that is that's the chance that X is less than 5. So how do we calculate greater than 5?
One minus the equation.
Right, so this is going to be Px greater than 5 is what I want. This is less than 5. Now, because it's a discrete distribution, you have to be very specific to tell it what you're telling it. So I want it to be less than or equal to 5. That should be the answer. 5 or less, but I want the answer for 1 minus. Okay,
Less or
what's that?
less or equal to 5 on the equation.
Yeah, less than or equal. Okay, so we have to be careful with discrete because the value, the probability at the value is meaningful. It's not just 0. So we have to be careful to remember to include that. Okay, so that's how we work with binomial. I'm going to teach you the formula for binomial. But basically, you can generate the whole distribution if you want in Excel. I'll do the same one, but okay, what I'll do is X. So it starts at 0, right? Because you could have no successes. So you always have to start at 0. I'm only going to do a few, but you could do all the 100 if you wanted. Excel has that power. Now, when I studied, I guess there was Excel in the 80s when I started studying, but in years before, in the 60s, anyway, in the decades before Excel, this was done manually. So actual tables were derived with these values. And now a function, or I'll teach you the formula to actually calculate these manually. Next class or whatever, you're going to see it in the videos. So I'm going to begin with the same thing, but I'm going to use this one here. Very small number. No, it stopped. So it goes D3, D4.
Yeah. You have to put a number. It's using 0 because you didn't put a number on the next one.
Oh yeah. Okay, yeah. So I'll just put the numbers in 3, 4. So you can generate the whole distribution and you notice, wow, it gets high very quickly.
Yes, because your probability was 10%, right? Or did you change that?
No, I didn't change it.
Right, so that's why it's going so so quickly up.
And so this is, let's go the other way. So this is gonna go up till 100. So let's see, 95, 96, 97, 98, 99, 100. So I'll explain how this formula works. So what it's doing is it's doing this cumulative. It's adding as it goes. Notice it's always adding the values. And I don't necessarily want that. I want to be able to see the value for itself. You see, because it's adding them all up. If I want to see that, I don't choose cumulative. I choose the other thing. I choose to say not cumulative. I do wrong. So this will be not cumulative. Let me specify. Anyway, so that I put a 0 here instead of a 1 that I put there, and then you'll see all the individual values as they go up and down. Okay, so that's the binomial distribution. Are you guys following what I'm doing here? So these are, I'm going to put a row in here. You want it not cumulative so you can see. Now, cumulative makes it easy to find the answers when you have to sum them. So it has a purpose. But if you want to see, this is the probability that X equals 5 umbrellas. The probability that X equals 6 umbrellas. Okay. This one over here is what?
Less or equal.
This is less or equal. So it's going to sum all of these before to make this one. All right. All right. Any questions? Okay, so that's just for you guys to play with, use. You can use it to solve problems, but you also need to know the formulas that I'm going to teach about binomial after. Okay. I also discuss Poisson and hypergeometric. I think this is not in the Bowerman book. I have to see the chapters, but I have to check my notes on that. But I've noted them. I'm not going to test you on Poisson and hypergeometric. I just introduce them as alternative distributions that also have parameters like n and p, but they use them differently, and they are very practical distributions. Poisson is used to describe weighting lineups and even waiting on the phone. Hypergeometric is a distribution that's used when you are sampling. It's often used for cards and casino, where you're thinking about diminishing a deck of cards or using up certain colors on the roulette wheel or numbers. So these are popular, but I'm not going to test you on them. All right. hypergeometric. So I just mentioned that they both have parameters, but they use them differently. All right, so I have a question here to help you. So what I really want to do in this part of the module is just help you identify binomial distribution as different from those other types of distributions, right? So a binomial has to satisfy the 3 criteria. So in this example about ESP is extrasensory perception. It's telepathy. So if you want to think about this experiment, testing to see if people have ESP, is this a binomial? Can you describe the variable known as the number of correct guesses that a person makes when they're shown 100 different cards with 4 possible symbols, and each of those symbols is equally likely to appear? So you imagine that a card is selected, and then the deck is reshuffled, it's returned to the deck. And so that is done with replacement as opposed to leaving the deck aside. So, or leaving the card aside from the deck. So each one has equal chance of occurring. There's 100 cards, and these images, star, circle, wavy line, or square, may appear. We're going to define a person to have ESP if they guess at least 50 cards correct out of 100. So where we define X as the number of correct guesses, is X a binomial? So we need to test. We need to verify these 3 criteria. In the first case, define what a success is and what a failure is. So success would be getting a correct or correctly guessing, right? And a failure would be an incorrect guess. And those are the only 2 possibilities, and nothing else will define the outcome. B, say you can test, you take the test and just guess all the way through. What's the probability that you will correctly guess 1 card? Well, as defined, I said that the 4 possibilities are equally likely. What is their probability?
25%.
It has to be 1/4, because in the sample space of 4 possible outcomes where 4 are equally likely, it's 1/4 plus 1/4 plus 1/4 plus 1/4, which makes 1. This is how I calculate the probability. So it has to be 1/4 or 25%. And how many independent trials will we have? That's right. So there's n equals 100 independent trials. And so we can write this as X distributed binomial, N is 100 and P is 0.25. All right, so those are the 2 basic discrete distributions I'm going to talk about: general discrete and the binomial, and the other 2 are just for illustrative purpose. The next set of distributions are the continuous ones. And we already talked about the normal distribution as a continuous distribution. And here's just an example. If I define the height of women 18 and over, that I can say has a normal distribution. I can give a range of possibilities, but really they are best described by a normal density curve. with a mean of 64, I think I used 64 inches, and standard deviation of 2. I have another example here. So now this might not be a normal distribution. The number of hours a student studied on a particular date, number of hours students studied before an exam. The sample space could be made up of a range of possibilities, and they can study for a fraction of an hour, right? So I'm going to introduce, this is a new distribution I introduced. It's called the uniform distribution. And the uniform distribution is also continuous, but its shape is a rectangular shape with a, it has a range of values 0 to 16 hours if you leave 8 hours for other things than studying. So this is my studying example. I define it as uniform and I use its parameters, the parameters that describe this well enough that I can derive probabilities from it are the lower and the upper bound. In our case, it's going to be 0 and 16. With that information, I can derive probabilities. And it's a matter of remembering how you calculate the area here. So this is a very easy example of continuous distribution. You don't need calculus. You just need some arithmetic and knowledge of area formula. And I have some other examples that I give you of different shapes for distributions that you can use. So you can practice with a continuous distribution, understanding that it's the area that represents the probability, not just the spike like it is for a discrete one. So I have a few exercises here. So I'm going to leave you guys here. If you haven't gotten this far, you can start here in your review this weekend and practice with the uniform distribution, get through these exercises. And for next week, you should have finished, because this is actually the material for Module 7. So I'm going to start Module 8 next week. But you should be comfortably ready to start 8. Let me just verify here. I want to verify on the platform my dates. Yeah, you should be done. You should be done by next week, Module 7. And then Module 8, we'll talk about next week. And I'll answer any questions you have. And then your test. I'm going to put up your test scores ASAP. I'm going to look at, because it looks like maybe there's an error in my grading scheme. So I'm going to double check that. So let's see, where am I here? I want to show you Moodle. It's funny, does it come up? Okay, I'll just do this. So you can see Moodle. And I have Module 8 scheduled for, okay, so yeah, we're going to start Module 8 next class. So you're going to work through all your probability stuff this week. And we'll talk about that a bit and then start Module 8 next week. But honestly, work diligently at your own pace. And I will highlight in our sessions, highlight the material where I think students may struggle or have misunderstandings. All right, so I'll say have a good week. I'll put this recording up if it helps, and I'll get your grades out.
Okay, have a good day, everyone.
Bye, everybody. I hope it
Bye.
helped. Ciao.
Yes, sir. Do you hear me?
Yes, yes.
I have a doubt because in the area of the grades of the course,